lot of different molecules have different kinds of shapes. If we just kind of click through, you can see a lot of different possibilities about what kinds of orientations these different kinds of molecules and ions can have. And so what we're going to do today is we're going to learn how to determine which of these shapes you're going to have. And we do it using this thing called valence shell electron pair repulsion theory, also known as VSEPR. Sounds like a big complicated term, but it's really not. If we were to take something like nitrogen, nitrogen has 5 valence electrons. So if we do a Lewis structure, we could imagine that it has 5 valence electrons, and each of these are valence. Now shell just means energy level. Electron pairs, that's a valence shell electron pair, that's a valence shell electron pair. There's only one there, so we wouldn't necessarily call it a pair, but these things are what we're looking at. And the idea is that they're going to repel one another because they're all negative. Things that have the same charge are going to repel one another. And that's the basic idea. We're going to use that basic fundamental truth about nature to determine and predict some shapes of molecules or ions. So how are we going to do this? Well, there's a set of steps. You could freeze frame there and write this all down. Won't make a whole lot of sense until we have worked it out. I don't want to sit here and wait for you to write it all down. We might need to freeze frame or come back. But we're going to start by drawing a Lewis structure. You can't do anything with determine the shape of a molecular ion until you've drawn a Lewis structure correctly. Yeah, correctly is kind of important. If it's not correct, it's probably not going to work. Then you're going to look at the center atom, but I'm not going to read these off. Let's go through an example as we go through here. So the examples, if you skip down to number 3, so let's just kind of go down to this chart. Number 3 refers to a chart. So we have this idea of these central pairs, and so let's look at some of these examples. One of the examples that it gives us here is CO2. So let's start with a CO2 molecule. This video is made assuming that you already know how to do Lewis structures. I'm not going to teach you how to do any of those here. You need to go back to one of the previous videos if you need help with that. So here is carbon dioxide. That is the correct Lewis structure for carbon dioxide. So we've got that covered, and now we can move to looking through the steps. First one is to draw a Lewis structure correctly. Now we're going to look at the center atom. We're going to count pairs of electrons around the center atom only. Counting a pair as a lone pair, a shared pair, or a double bond, or a triple bond all count as one. It doesn't matter. So here we go. There it is. And we look at the center atom. The center atom in this case is carbon. And so we look and we see there's a pair there. It's actually 2 pairs, but since they're together, we only count them as 1. And there's another pair. So we have 2 pairs around the center for carbon dioxide. And so we go back to our chart and we say, well, what does our chart tell us about that? Our chart tells us that for 2 pairs, we're going to get a linear electron geometry. Electron geometry for 2 pairs is linear, which means that the bond angle is 180, and the example would be CO2. Well, where does this all come from? Well, it comes from this idea that VSEPR, valence shell electron pair repulsion, we have around the center atom, we only have electrons here, and they want to be as far apart as possible. So the idea here is that they are going, if this is the carbon atom here in the middle, they're going to arrange themselves as far apart as possible. And so, you know, if we have a pair, you know, represent the pair with like a little lobe here, we have a pair on each side. Now that's as far apart as they can get. If one of them goes that way or that way, you know, now they're going to be rotating towards the other, and they don't like that. They want to be pointing straight away from each other, 180 degrees. And so that's where that shape comes from. Now if there's 3 pairs, we can sort of imagine that. There are some examples there for 3 pairs. 3 pairs, the farthest they can get away from each other is going to look something like this. It's almost like sort of a peace sign kind of thing. And I'll show you a better example here in a little bit. In fact, let's go ahead and do that now. Let's look at some of these examples. If we look at 4 electron pairs, I'm sorry, we were doing 2 pairs. There's CO2. You can see that this electron pair, these little gray dashes represent electron pairs, shared pairs, bonds here. And so these are 180 degrees away from one another. That's as far apart as they can get. If you had a 3rd pair, well, now you can see that kind of looks like my peace sign that I had a second ago. Now, if this were to rotate that way, it would be closer here. And any way you would move these, they would get closer together. So this is their ideal situation. And so if you had something with 4 pairs, and by the way, the bond angle here is 120 degrees. If you're not sure where that comes from, it's all the way around here would be a circle, would be 360 degrees, but it's cut up into 3 parts, so 360 divided by 3 is 120 degrees. So that's what 3 pairs would look like if we go back to our chart and just kind of keep total here. We've got 2 pairs around the center, would be a line. 3 pairs is 120 degree angle. We call that trigonal planar. So that shape, we were just showing you this shape here. This is trigonal planar because it's triangular in shape, but it's in a plane, P-L-A-N-E. It's a plane. It's flat. It has not. It's not like a pyramid, or it's not raised at all in the middle. It's very flat. Now, what about 4 pairs? Well, the 4 pairs, if we go back and look at those, 4 pairs are going to look something like this. Now, this is a little bit harder to visualize on paper. You almost need a 3-dimensional model like this. I have some physical models you can look at, but you can't take those with you. So the computer is about as good a way as you can do this. So you got 4 pairs around there, and that's those electrons, those gray bond things, are going to orient themselves in that way. So you can see that it's kind of a it's almost like a tripod or something, like a lunar landing vehicle or something. And the bond angles here are 109.5 degrees there. And so these are all showing you where the electron pairs will be based on how many pairs there are. But, and we've only looked at pairs. If you, no matter what example you're doing, if you count pairs, let's go back. No, let's not go back. We'll go back. We'll do that later. So once you know the electron geometry, you can then determine the shape of the molecule, which is really what we're interested in. So this part is the tricksy part. This is where people stumble a little bit. Most people can, with a little practice, they can get this stuff just fine. It's the molecular shape they get a little confused. And here's a big thing to remember. The molecule, if you want to know the shape of the molecule, you want to look at the atoms, not the electrons. Atoms, not electrons. So the molecular shape is not the same thing as the electron geometry necessarily, although it can be the same. And so as we go through some examples here, this will begin to make a little bit more sense. So let's look at some of these examples. Let's look at SO2, and let's look at SO2. If we do SO2, the Lewis structure for SO2 is going to look like this. You're going to have S dash 2 and O dash 2 and O, and then you're going to have a double bond on one of the O's and a single bond on the other. So if we count that up, we got 2, 4, 6, 8, 10, 12, 14, 16, and I believe if we count it up we use 18, but that's okay because the sulfur in the middle is not happy yet. It needed 2 more anyway. So now we've got 18 total valence electrons and everybody's happy. So if we go back to counting around the central atom here is sulfur, and sulfur has one place where there's electrons, 2 places, 3 places. So it's got 3 pairs. And so the electron geometry, if we go back to our chart, should be, so it's got 3 pairs, and so if you go back to the chart, it's going to tell you that 3 pairs is a trigonal planar, 120-degree bond angle. And we knew that would come out this way because we were doing SO2 as our example. So what does that tell us? It tells us that if we go back and look at that particular molecule, it should have this trigonal planar geometry, 120-degree bond angles. So SO2 has an electron geometry of trigonal planar, but it has a molecular geometry that is different. Well, why is that? Well, if we look here, SO2, we have an atom in the center that's a sulfur. It's connected to an oxygen atom, and it's connected to another oxygen atom, and it's connected to a lone pair. Well, the lone pair is not an atom. It's not part of the molecular shape, so we can ignore it. So while the electrons make a shape of trigonal planar, the atoms do not. The atoms just make this shape, whatever shape that is. And we tend to call that, pretty creatively, we call it a bent line. Generally speaking, we call that a bent line because if there were an atom attached here, well, now it would be a trigonal planar, but it's not. So that would be one example. If you have 3 pairs around the center atom, but only 2 are attached to atoms, then you'd have a bent line. And there are a lot of other permutations as well. If you have, for example, so here we kind of work through some examples. If you have CO2, that's an example of something that has 2 pairs, 2 electron domains, and therefore, and each one is attached to an atom. So there's the grays are the electrons, and then the atoms are attached to the ends like that. That would be an electron geometry of linear, but since each electron is attached to an atom, it also is linear. In fact, all linears turn out to stay linear. Anytime your electron geometry is linear, your molecular geometry is also linear. But that's not true for some others. Let's do a trigonal planar. If you have a trigonal planar, here's an example. SO3 has 3 electron pairs, trigonal planar geometry, and each one is attached to an atom, so the molecular geometry is trigonal planar, as it says over here. However, let's look at SO2, the one we just did. SO2, if we look at it in a full-scale model, if you look at electrons, here's the lone pair, and here's a shared double bond, and here's a single bond. So each of these counts as 1 electron domain. So you have 1, 2, 3 pairs around the center atom, but only 2 of them are attached to atoms. So the electron geometry is still trigonal planar because of the electron geometry there's 3 pairs, but the atoms themselves, there's not an atom up here, so you can't count that as part of the shape, and you're left with just the bent line shape. The same thing can happen with 4 pairs. Here are 4 pairs all connected to atoms, so the molecule is a tetrahedral molecule. But here's an example of a molecule which, if you do the Lewis structure, you'll see that there's 4 pairs, but 3 of the pairs are bonded to atoms, and 1 of the pairs is lone pair. It's not shared. There's not an atom up there, so you ignore that. This has a name. This is an important one to know. The name of this kind of shape is Trigonal Pyramid. So this is kind of your first video on just how to connect molecular geometry to electron geometry. And so you got to kind of work through examples until it all makes sense.